this video, I want to expand on the topic of simple harmonic motion. Now, simple harmonic motion can be defined in one way, in an example system, as a mass hanging from a spring, as shown on the screen here. And where we left off in the last video was to say that the differential equation defining this situation looks like this: mx double dot, which is the acceleration, plus the spring stiffness times x equals 0. Now, we're going to redefine this equation a little bit by saying that the natural frequency of a system can be defined as omega n, and it's equal to the square root of k over m. Now, if I define this variable omega n, I can go ahead and rewrite my differential equation then as x double dot plus omega n squared x equals 0. And this is what we would call the standard form of the differential equation representing simple harmonic motion. Now, this differential equation is something that we can go ahead and solve. And I'm not going to walk through the derivation of that solution. Instead, I'm going to say that if we solved this, we would get a general form solution by taking the double integration for x as equal to c1 sine omega nt plus c2 cosine omega nt. Now, c1 and c2 here are constants of integration. So they're those constants that you get when you perform an integral that doesn't have defined limits. And these two constants, c1 and c2, are going to be defined eventually here by our initial conditions. So once we know our initial conditions for any given system, we would plug those in and get c1 and c2. So before I get to that point, though, I want to show what would happen if we take now the derivative of this solution in order to calculate the velocity and the acceleration. So first, if I take the first time derivative of this equation x, I would end up with c1 omega n cosine omega nt minus c2 omega n sine omega nt. And I can do it again by taking the second derivative, and I'm going to get an equation of the form minus c1 squared sine omega nt minus c2 omega n squared cosine omega nt. So I've taken one time derivative and then a second time derivative in order to calculate and solve for x dot and x double dot in this case. And I could double check this solution and make sure that these are all valid solutions to my differential equation by plugging x back into my initial differential equation and plugging x double dot into my differential equation. I could see that that solution should fall out as being correct. So now I want to think about, well, what happens? How do I get these constants of integration out of there and put them in terms of something more usable? Well, in general, for most problems, we can set the time, the initial time, to be 0. So we define a specific position at t equals 0 and say that x at that time at t equals 0 is equal to some initial position, x naught, and v at t equals 0 is equal to some initial velocity v naught. So it would be common, perhaps in a solution procedure, to know the initial position and the initial velocity before we would go ahead and solve anything. So now if I take these two conditions, t equals 0 and x equals x naught, and plug that up here in my solution for x, and do the same thing for velocity, t equals 0 and v equals v naught, and plug that into the second equation, what I end up with is a solution for C1 in terms of V naught and omega n, and for C2 as x naught. So that allows me to have more useful information that I can plug back into these equations and have these constants of integration be in terms of my initial conditions. Now, of course, this is, again, using the assumption that I have some v naught and some x naught defined at time t equals 0 that I can make use of. All right, so looking at the equation for x, we can quickly realize that if I were to plot x versus time, I have a simple sinusoidal function. And it's not a very good drawing of a sinusoidal function, but I think you get the idea. And this sinusoidal function has a few properties that I might want to define. So first, for example, I might measure the period of the oscillation, which is the time that elapses from peak to peak. So given that I have a repeating pattern of my variable x, how long does it take for that pattern to repeat? So I'm going to measure from peak to peak in this case. I could similarly measure from valley to valley and so forth. So this tau is defined as the period of the oscillation, and it's also equal to 2 pi over omega n if omega n is the natural frequency in radians per second. And of course, then it's going to have units of seconds, which is the time that we measure. I might also want the natural frequency defined in terms of something we'll call Fn, which is specifically 1 over the period, and therefore also omega n over 2 pi, with units of 1 over seconds, which is the same thing as a hertz. So in this case, I have two definitions for the natural frequency, omega n, which is in radians per second, and Fn, which is in hertz, and both are really defining the same general thing, just changing the units there. Now, pretty much every object has a natural frequency of this form. Stiffer objects will have a higher natural frequency, meaning that if I were to displace them, if that spring was stiff and I displaced it, it's going to vibrate very quickly. If it's a relatively loose spring and I displace it, it's going to vibrate more slowly. So we can measure that, we can define it, we can calculate it, depending on the principles of what we know about the situation. All right, I'll stop there. Thanks.